Why don't my experimental vibration results match my Fey model? Imagine tuning a musical instrument and finding the sound different from what you expected. That's similar to what happens when experimental vibration results don't match your finite element model predictions. It can be puzzling, but understanding the reasons behind these differences can help you improve your analysis. First, models are built on simplifications. When creating a finite element model, you often assume ideal shapes, uniform material properties, and perfect boundary conditions. But in real life, materials can vary in stiffness or damping, and supports might not be perfectly rigid or fixed. These small differences can shift the natural frequencies and change the vibration modes you observe during testing. Second, uncertainties in parameters play a big role. For example, the mass distribution might not be exactly known because of manufacturing tolerances or assembly variations. Damping, which dissipates energy, is especially tricky to model accurately. If your model uses simplified damping assumptions, it might not reflect how the structure actually behaves, leading to mismatched amplitudes or resonance widths. Third, the quality of your mesh matters. If the finite element mesh is too coarse, it might miss critical stress concentrations or the true shape of vibration modes. A poorly refined mesh can produce inaccurate results or numerical artifacts. Running mesh convergence studies, gradually refining the mesh until results stabilize, can help ensure your model is capturing the real behavior. Fourth, experimental setup differences can cause discrepancies. Sensor placement, excitation methods, and environmental noise can all influence measurements. If the test does not excite all the relevant vibration modes, or if sensors are not positioned correctly, some modes might be underrepresented or distorted. Proper testing procedures and multiple measurements can help get a clearer picture. Fifth, the way you compare results is important. Simply matching frequencies and mode shapes might not tell the full story. Using advanced correlation techniques to compare parameters like stiffness, damping, and mass helps identify where the model needs adjustment. This process is called model updating, and it makes your Fey model more reliable. To improve the match between your experimental data and your finite element model, start with detailed mesh refinement and ensure your material properties are as accurate as possible. Incorporate variability in your parameters to account for real-world differences. Model boundary conditions carefully to match how the structure is supported during testing. Use more sophisticated damping models or measure damping directly from experiments. Make sure your testing setup excites all relevant modes and place sensors carefully. Finally, use parameter updating techniques to fine-tune your model based on experimental results. Remember, finite element models are approximations, and experiments have their own uncertainties. The goal is to reduce the differences as much as possible through iterative improvements. This approach is a key part of professional practice in vibration analysis and helps you develop more accurate and reliable models for real-world applications.